Hi everyone, thank you for joining me today. Welcome to another presentation in Chem Safety's online webinar series. Today we're going to be looking at managing pesticide exposure in the workplace. My name is Paul Robertson. I'm the Managing Director at Chem Safety and I'll be your presenter today. Please feel free to send any questions regarding the webinar through to info@chemsafety.co.nz after the webinar is finished and we'll aim to get back to you. Our details will also be on the follow-up email, which also includes a link to the recording of today's session. Just a quick disclaimer before we get into it. The information provided in this webinar is for educational and general awareness purposes only. It's not intended to replace or substitute for professional advice, site-specific risk assessments, or legal obligations under New Zealand law. So just a quick overview of the topics that we're going to discuss in today's webinar. Firstly, we'll take a look at what pesticides are, including the different perspectives of the public versus the commercial or technical sector. In the health effects section, we'll look at some of the common symptoms of pesticide exposure and how they can affect our health. We'll then briefly cover some legal obligations around pesticide handling, storage, and protecting worker health. Then we'll move on to how people are exposed to pesticides, including routes of entry into the body and particular high-risk tasks. Following that, we'll take a look at how we can evaluate pesticide exposure and some controls that can minimize exposure. Then we'll run through a case study of spraying pesticides in a greenhouse and illustrate how an occupational hygienist would typically evaluate the risk from start to finish and demonstrate the occupational hygiene cycle in action. So pesticides are chemical or biological substances used to prevent, control, or eliminate pests. The term pest includes anything that can harm crops, livestock, property, or the health of humans or animals. Common occupational settings where pesticides are used are agriculture, horticulture, pest control, greenkeeping, and turf maintenance. All of the following are different types of pesticides. Insecticides control insects like mosquitoes, beetles, or moths. Herbicides control unwanted plants or weeds. Fungicides prevent or kill fungi, molds, mildews, or rusts. Rodenticides control rats and mice, and bactericides target harmful bacteria. The way we view pesticide use from an occupational hygiene perspective or a technical perspective differs from that of the public perspective. However, the public perspective should not be ignored, as pesticides can pose risks to people, animals, and the environment. Traces can sometimes remain on food, drift into nearby areas, or accumulate in soil and water. Bees, fish, and other non-target species can be harmed if pesticides aren't managed carefully. That's why safe use is essential. Key steps for use of pesticides at home are to follow label instructions, wear protective clothing if handling them, store them securely and away from children. The key message for the public: pesticides are useful tools, but they need careful, responsible use to keep people and the environment safe. From an occupational hygiene perspective, pesticides are chemical hazards that can expose workers through inhalation, dermal absorption, and ingestion. The degree of risk depends on the toxicity of the active ingredient, for example, organophosphates versus pyrethroids, two different active ingredients and two different toxicities. The formulation matters, so liquid concentrates versus powders versus fumigant gases will all impact on their toxicity. Application method, spraying versus aerial drops, enclosed space fumigations will also have an effect. Duration and frequency of exposure also has an impact on the risk of exposure to people. And critically, what control measures are in place? Occupational hygiene focuses on risk assessment of tasks and exposure levels. The key message in the occupational hygiene context: pesticides should be treated as hazardous chemicals, requiring structured controls to protect workers in the surrounding community. Pesticides are designed to kill pests, but some pesticides can also cause health effects in people. Workers exposed to pesticides can experience a wide range of health effects, from immediate mild symptoms to severe long-term illnesses. The type and severity of these effects depends on the pesticide, the amount of exposure, and the duration of the exposure. Most often, pesticides affect the nervous system, That's the system in your body that controls your nerves and muscles. Acute health effects appear quickly, from within minutes to a few days after a single or short-term exposure. Symptoms to look out for are often directly linked to the poisoning event and can range from mild to life-threatening. The table on the slide shows that pesticide exposure can result in a wide range of health effects, from mild effects including headache, nausea, thirst, and sweating, to moderate effects, vomiting, coughing, blurred vision and mental confusion, to severe, including inability to breathe, chemical burns, unconsciousness, and death. When we talk about the health risks of pesticides, we often think about those acute effects, things like nausea and dizziness or skin irritation that happen straight after exposure. But an equally important issue is the chronic effects that can develop over time. Chronic effects are health problems that build up gradually, sometimes over years of repeated exposure. They can be much harder to spot because symptoms are often subtle at first. Let's take a look at some examples. Certain insecticides, especially organophosphates, have been linked to neurological problems such as memory loss, mood changes, or reduced coordination. Repeated inhalation of pesticides can lead to respiratory disease, including asthma or chronic bronchitis. Skin disorders like dermatitis or allergic sensitization may occur in workers with long-term dermal exposure. There are also concerns about reproductive and developmental effects, including reduced fertility and birth defects, particularly from some herbicides and fungicides. Research has found association between pesticide exposure and certain cancers, such as non-Hodgkin lymphoma, leukemia, and prostate cancer. Finally, some pesticides act as endocrine disruptors, meaning they interfere with hormones which can affect growth, metabolism, and overall health. The important message here is that chronic effects may not be obvious in the short term, but they can be very serious. That's why prevention, protective equipment, and ongoing health monitoring are so critical when working with pesticides. Here's a quick overview of New Zealand's legal obligations covering pesticide use, focusing on the Has No Act, Health and Safety at Work Act, and its hazardous substance regulations. The Health and Safety at Work Act is New Zealand's modern workplace health and safety framework. It emphasises risk identification, management, and proactive duty holders. As per the Health and Safety at Work Act and associated regulations, PCBUs are required to identify hazardous substances present in the workplace and maintain an inventory, assess and manage associated risks by applying the hierarchy of controls, provide training, supervision, information, and access to safety data sheets to all workers using hazardous substances, ensure proper labelling, signage, container standards, and packaging for stored or decanted substances, implement plans for emergencies along with the required response protocols, review controls frequently, especially after changes or incidents. For certain high-risk substances, the regulations require PCBUs to appoint or provide certified handlers. These are individuals holding a certificate issued by a compliance certifiers licensed by WorkSafe, which demonstrates required competency. For pesticides, this is required for HASNO classes 6.1A and 6.1B toxic substances, and also required for some other named substances. Specific qualifications are also required for highly ecotoxic agrochemicals. Vertebrate toxic agents and fumigants may require controlled substances licenses. For specified classes of pesticides, additional obligations may arise, such as record keeping of applications, including details like location, quantity, wind parameters, user identity, and environmental control measures. Storage of flammable, toxic, and corrosive substances above a threshold quantity will also require location compliance certification. The overarching purpose of the Hazardous Substances and New Organisms Act, or HASNO Act, is to protect the environment and the health and safety of people and communities by preventing or managing the adverse effects of hazardous substances and new organisms. Key aspects of what the HASNO Act regulates include risk assessment. It requires a consistent science-based process to assess the risks, benefits, and costs of introducing hazardous substances and new organisms into New Zealand. Approval and regulation. All hazardous substances and new organisms must be approved by the Environmental Protection Authority before they can be imported or manufactured in New Zealand. The Act sets out a range of controls for their use, storage, transport, and disposal. Agrochemicals must have individual approvals. There's also a classification system that defines a hazardous substance based on a range of intrinsic properties. In 2021, New Zealand moved to the GHS, or Globally Harmonized System of Classification. So let's take a glance at the key agencies and their legal responsibilities. The EPA, or the Environmental Protection Authority, approves pesticides under the HASNO Act for import, manufacture, or supply. It sets controls via EPA notices, including environmentally hazardous substances disposal and labeling, and it oversees non-workplace regulations. WorkSafe New Zealand enforces workplace chemical safety under the Health and Safety at Work Act and hazardous substance regulations, oversees certification, compliance, guidance, and inspections, and manages safe work instruments for substances requiring technical specificity. Local councils may also regulate hazardous substances in the public or environmental context via bylaws, the Resource Management Act, and the HASNO interface. So let's take a look at the routes of exposure. How can pesticides harm us? And how can they get into our body? Pesticides can enter the body in a few different ways. It's really important that we understand them so that we can protect ourselves properly. The most common route of exposure in the workplace is through the skin. When we mix, load, or spray pesticides, small splashes, spills, or even residues on plants can get onto our hands, arms, or clothing. The skin can absorb these chemicals, and absorption is even faster if the skin is sweaty, cut, or not protected. A consistent pattern in virtually all studies on occupational pesticide exposure is that the dermal dose exceeds the respiratory dose by ratios of between 50 and 1,000 to 1. This is because pesticides typically have a low vapor pressure and high dermal absorption rates. A dermal to airborne dose ratio of 100 to 1 is a good first approximation for many open uses of low volatility pesticides. The next important route is inhalation, breathing in pesticide vapors, fine sprays, or dust. This is especially risky when spraying in greenhouses or enclosed spaces, handling fumigants, or working in areas without good ventilation. Ingestion or swallowing usually happens by accident. If someone eats, drinks, or smokes without washing their hands properly, small amounts of pesticide can be transferred into the mouth. And finally, ocular exposure through the eyes. This can happen if there's a splash, drift, or someone rubs their eyes with contaminated gloves. The eyes absorb chemicals very quickly, so this route can be particularly dangerous. The key message here is most occupational exposures happen through the skin, but all four routes are possible. That's why we need to combine protective clothing, good hygiene, and safe work practices when working with pesticides. Let's take a look at the hazard hierarchy of controls so that we can see the order of the most effective controls for pesticide use. Obviously, elimination is the most effective, ceasing the use of a hazardous pesticide altogether. So sometimes this can be achieved by a decision to stop growing a certain crop or using a pest management method that doesn't require chemical intervention. Substitution involves replacing a highly toxic pesticide with a less hazardous or non-toxic alternative. For example, using a biological pest control method like introducing beneficial insects or biopesticide instead of a conventional chemical. Engineering controls. These controls are designed to physically isolate workers from the pesticide. They are built into equipment or the work environment itself. Isolation can include closed mixing systems, using equipment that allows pesticides to be transferred from the container to the sprayer without the worker's direct exposure. This is crucial for liquid concentrates. Enclosed cabs, providing tractors or application vehicles with sealed enclosed cabs that have a filtered air supply to prevent airborne pesticides from entering the operator's breathing zone. Ventilation can be useful using fans and other ventilation systems to move pesticide vapors away from the worker, especially in enclosed spaces like greenhouses. Automated application systems, another great control for taking the worker away from the substance. So utilizing automated sprayers or irrigation systems that apply pesticides without the person needing to be present in the treated area. And then administrative controls, we're getting less effective in the way they prevent exposure as we move down the inverted triangle there. So administrative controls are changes to work practices and procedures that reduce the risk of exposure. They rely on worker training and management. Workplace procedures are included in administrative controls. They involve implementing clear written procedures for mixing, applying, and cleaning up pesticides. These include reading and following the product labels and following in-house rules and restrictions. Worker training, providing comprehensive training on the hazards of pesticides, safe handling procedures, and correct use and maintenance of all equipment and personal protective equipment. Restricted entry intervals are another administrative control. So establishing and enforcing strict re-entry intervals, which are mandatory waiting periods after a pesticide application before workers can safely re-enter a treated area. Worker rotation, scheduling workers to rotate between tasks to reduce the amount of time that any one person is exposed to a hazard. Personal protective equipment is at the bottom of the triangle there. It's the least effective control if it's a standalone control. So personal and protective equipment must be used as well as all of the other controls that sit above it for it to be effective. So PPE is the last line of defense and should be used in combination with other controls. Creates a barrier between the worker and the pesticide. PPE is considered the least effective control because it can fail. So you can get a rip in a glove. Someone's filters don't get replaced in their respirator, or there's damage to a respirator and it means that the worker can be exposed. So if we look at some useful PPE for working with pesticides, some of the most critical parts are chemical resistant gloves. So hands are the most common route of exposure, so the type of glove should be specified on the pesticide label. Coveralls and aprons, long-sleeved chemical-resistant coveralls or aprons to protect the skin and clothing from splashes and drift. Really great for protecting the worker from exposure. Think about eye and face protection. Remember we said that eyes are an excellent way for the body to uptake pesticides, so goggles or face shields to prevent splashes or mist from entering the eyes. Respirators obviously worn to protect the respiratory system from inhaling pesticide mist, dust, or vapors. Type of respirator is determined by the pesticide and application method. And don't forget fit testing and respiratory protection programs for people using respirators. So let's have a look at fumigation, because fumigation is a very specific type of pest control that we use in New Zealand. It's quite different from the way that most pesticides are applied. So at its core, fumigation means using a toxic gas to control pests. It's often used for things like timber treatment, stored fruit, or inside shipping containers. The common fumigants we see in New Zealand include methyl bromide, phosphine, and sulfuryl fluoride. Because we're dealing with gases that are highly toxic, fumigation is tightly regulated. The HAZNO Act, the Health and Safety at Work Act, and EPA controls all apply. You need to be a certified handler and usually a licensed fumigation operator to legally carry it out. The fumigation enclosure must be properly sealed, monitoring of gas concentration is required, and ventilation has to be managed before anyone can re-enter. There are also often buffer zones required to keep the public safe, and operators must keep full records of each fumigation. Now, if we compare fumigation to regular pesticide application, the differences are pretty clear. With fumigation, you're working with gases in an enclosed space, not liquids or granules applied to plants or soil. The toxicity of fumigants is generally higher, which is why they require special certification. The main exposure risk is inhalation of the gas, whereas with routine spraying, the biggest risk is dermal contact or spray drift. Another key point is that fumigation absolutely requires gas monitoring and clearance testing, while with spraying, monitoring usually focuses on residues or drift. So the takeaway here is fumigation is a high-risk, highly controlled process and very different from routine spraying. It's a specialist activity and it comes with extra responsibilities for safety and compliance. When we talk about pesticide exposure, it's not enough to just assume risk. We need to measure and confirm how much exposures workers might be actually getting. There are a few key ways we do this. First, observation and task analysis is critical. We look closely at how pesticides are mixed, applied, and cleaned up. Often just by watching the work process, we can identify points where contact or inhalation is most likely to happen. Next, we use exposure monitoring. This could mean air sampling using personal pumps or passive badges that workers wear to measure what they're breathing in. We can also take wipe samples from surfaces or equipment to check for contamination. A third method is dermal exposure monitoring. Because skin contact is the most common route of exposure, we sometimes use patches or dosimeters on clothing or skin to measure how much pesticide lands on the body. Fluorescent tracer dyes can also be sprayed to show under UV light where the pesticide is depositing on clothing or skin. We also have biological monitoring, which looks inside the body. For certain pesticides like organophosphates and carbamates, we can test blood or urine for changes or breakdown products. Cholinesterase monitoring is a good example. It shows whether workers' enzyme activity is being suppressed by exposure. Finally, we review records, product labels, and past incident reports. Past monitoring data or health checks can also reveal whether existing controls are working or not. The key idea here is that no single method gives the full picture. By combining observation, measurement, and health checks, we can get a clear view of exposure risks and decide on the best controls to protect workers. Let's take a look at an example scenario and work through how we could assess the risk from an occupational hygiene perspective. So in this scenario, 2 staff members are applying a pesticide spray, which we've called X, in a large enclosed greenhouse on a commercial site. For the pesticide type, you've got a safety data sheet for the product, which we're going to have a look at on the next slide. The workplace is a large enclosed commercial greenhouse. The task, 2 staff members are applying the pesticide via backpack sprayers. The work duration is 3 to 4 hours. The environment is an enclosed space with limited ventilation and high humidity. Formulation for the pesticide is a liquid concentrate mixed with water applied as a fine spray. Safety data sheets can contain some useful information on product handling. We can see here that the spray contains carbaryl, which is a carbamate-based insecticide. There is a New Zealand workplace exposure standard for this compound of 5 milligrams per cubic meter. That can be useful if you're doing any air monitoring around the process. You can see the substance is very toxic to humans, a suspected human carcinogen, harmful to specific organs or systems within the body, and also harmful to the environment in several different ways from the HAZNO codes. Safety data sheets also contain useful information on the safe handling and storage, and some controls and personal protective equipment are also recommended. For example, wear protective gloves, safety goggles, suitable protective clothing, and respiratory protection when using in poorly ventilated areas. Hand washing before breaks, keeping the product away from food, and changing out of contaminated clothing are also recommended. Carbamates are reversible cholinesterase inhibitors. Acute health effects of exposure include headaches, dizziness, and nausea, and other respiratory distress. Chronic exposure can lead to neurological issues and possible reproductive effects. So it's important to consider the most likely times that workers can be at risk. A general rule of thumb for assessing risk is that the more concentrated the pesticide or harmful chemical is, the greater the risk. Therefore, there is particular risk of exposure during mixing and dilution of concentrated pesticides. Spraying may lead to inhalation of aerosol droplets and dermal absorption through clothing and bare skin. Re-entry is also another risk activity. So if workers re-enter a greenhouse too soon after it's been sprayed, they may be exposed to airborne residues or contaminated surfaces. So identifying the routes of exposure is partly what we just talked about, but let's just summarize. So inhalation, fine mist, aerosol, aerosols are suspended in the enclosed greenhouse air. Dermal, likely significant due to backpack leakage, spray drift, sweat-soaked clothing. Because we were working in a high humidity environment, so that having sweat-soaked clothing will increase the uptake of sprays through the skin. Ingestion, there's a secondary risk if eating or drinking without proper decontamination. So make sure you look out for good hygiene facilities and work behavior at break times. The following observations were made during the site visit to assess the task. So workers wore standard cotton overalls and cotton gloves, not chemically resistant. Respirators were available, but not consistently worn. Workers also were observed with facial hair, which reduces the effectiveness of respirators. The ventilation system for the greenhouse was not in operation during spraying. No signage or restricted entry protocols were in place. No hand washing station in the close vicinity of the greenhouse. Workers were observed to be smoking while on breaks between spray application. So initial judgment in this case, it's a very high risk scenario. There's poor PPE compliance, inadequate ventilation, and no procedural controls to mitigate the risk of exposure to the workers. So moving on to a quantitative risk assessment. Typically just the qualitative assessment would be enough in this type of review, because we've identified that it's very high risk, and ideally putting controls in place before moving to the quantitative risk assessment would be good practice, but for the purposes of this scenario, we're just going to go straight through the whole process so you can see what it's like. So air monitoring was undertaken, so personal sampling during spraying to measure aerosol concentration. Dermal monitoring was also undertaken, which was in the way of cotton glove dosimetry and wipe sampling of exposed skin areas after the task. Biological monitoring was undertaken to look at the blood cholinesterase activity before and after spraying shifts to identify overexposure. Reference standards that are useful to look at here are the workplace exposure standards for Cabarrel, WorkSafe New Zealand BEI, so recommended action: if there's less than 60% of baseline cholinesterase activity, suspend worker from working with pesticides. If there's less than 80% of baseline, repeat the test to confirm result. If greater than 75% of baseline, permit a previously suspended worker to recommence normal duties. So findings after the monitoring showed that air monitoring pesticide mist levels were around half of the workplace exposure standard. Glove dosimetry indicated high dermal uptake consistent with sweating and spray deposition. One worker showed mild cholinesterase depression on biological monitoring. So existing controls, cotton gloves, cotton overalls, and inconsistent respirator use, facial hair, and hygiene practices are not adequate to control exposure. So similar conclusion to the qualitative assessment. So here are some recommended control measures based on the findings. So firstly, always look at elimination and substitution. So can a less hazardous product or biological alternative be used instead of the spray? If not, let's move to engineering controls. So simple ones would be to improve the greenhouse ventilation during and after spraying. Can spray systems be improved to be more leak resistant, create less aerosol in the worker's breathing zone? Work practices and administrative controls include training staff in the mixing and loading of chemicals, or using closed transfer systems if available. Establish hygiene protocols, wash hands, no food and drink in the spray area. Implement signage and access control during and after application. So establish re-entry interval of 24 to 48 hours post-application. That interval will depend on the type of spray that's being used. Rotate staff to reduce duration of exposure. PPE, importantly, provide chemically resistant gloves, nitrile or neoprene. Ensure the use of properly fitted respirators, and make sure that you have a respiratory protective equipment program to manage all of the respiratory protective equipment. Continuous review. So let's take a look at how this case shows how hazard knowledge, task analysis, exposure monitoring, and control verification come together in occupational hygiene. Even common practices like spraying in a greenhouse can create high exposure risks if controls aren't well implemented. This case study is a good example of the occupational hygiene cycle in practice. Anticipation is thinking about what hazards might exist before we even step on site. This is about foreseeing potential hazards based on knowledge of processes, materials, and work environment, and involves reviewing chemical inventories, safety data sheets, process descriptions, staying updated on emerging risks, new pesticides, and regulatory changes. Predicting where hazards could arise, e.g. in pesticide application, anticipating risk from mixing concentrated chemicals or spraying in poorly ventilated spaces. Recognition is observation of which hazards are actually present in this workplace and is the step of identifying hazards that truly exist in the workplace. Activities involved include site walkthroughs, worker interviews, reviewing incident records, observing tasks where exposure is most likely, for example, mixing, spraying, and re-entry. Using your senses to recognize physical signs, strong odors, visible residues, lack of PPE use. Evaluation is determining how much risk does this hazard actually pose, and is about quantifying the level of worker exposure and health risk. Activities for evaluation include exposure monitoring, so your ear monitoring, your dermal wipes, or biological monitoring, comparing exposure data with workplace exposure standard or biological exposure indices. If no standards exist, which can be common for pesticides, compare the data to toxicological benchmarks or use qualitative risk matrices. Control is the practice of eliminating or minimizing the risk and involves implementing strategies using the hierarchy of control. And the cycle is continuous. The process doesn't stop after controls are in place. You reassess. Did exposures decrease? Are workers following the procedures? Have new hazards emerged? For example, was a new pesticide introduced? Occupational hygiene is a loop. Anticipate, recognize, evaluate, control, then cycle back again. So key takeaway messages from this webinar. Pesticide use is common in New Zealand workplaces. Try to choose safer options first. If you can, use less hazardous products or alternative pest control methods. Use the right equipment, enclosed cabs, low drift nozzles, and good ventilation keep spray where it should be. Follow the rules on timing. Respect no entry periods, post warning signs, and keep others away until it's safe. Wear the right gear. Gloves, overalls, and masks or respirators to protect you when nothing else can. Always check they're in good condition and take special care to protect the skin from exposure. Special care with fumigation. Only trained, licensed people should do it. Never enter until it's cleared. Look after your health. Some sprays affect your body, even if you don't notice straight away. Health checks may be needed for some products. Know the law. Follow product labels, safety data sheets, and New Zealand rules, especially the HASNO and health and safety at work laws. Safe spraying helps everyone. It protects you, your family, and your workers, your neighbours, and the environment. Keep up with training and maintenance of equipment. Maintain your equipment and replace gear when it's needed, and refresh your training regularly. Thank you for joining me on today's webinar. Please remember to send any questions through to info@chemsafety.co.nz.